Welcome to the Explainer. Today, we're diving straight into the hidden, intensely complex architecture that actually powers massive modern video games. Have you ever wondered what keeps a game from stuttering when absolute total chaos breaks out on your screen? Well, it all comes down to some incredibly brilliant computer science, and today we're going to unpack exactly how it's done. So think about it. How do real-time simulations, whether we're talking about a sprawling open-world game or a hyper-realistic physics model, how do they process millions of objects in literal milliseconds without a single hitch? It's a massive engineering hurdle. And the secret here, it doesn't lie in just throwing faster hardware at the problem. It actually lies in how developers fundamentally structure their data under the hood. Here is our roadmap for today's journey. First, escaping the OOP trap. Second, the anatomy of an ECS. Third, the concurrency bottleneck. Fourth, the ABC problem. And finally, number 5, enter the entity FSM. Okay, let's jump right into part 1, escaping the OOP trap. Let's travel back for a second to 1998. The developers of a game called Thief: The Dark Project realized that deep, traditional, object-oriented hierarchies were literally strangling their game's performance. To escape that trap, they pivoted to data-oriented design, or DoD. This paradigm is a total shift in focus. Instead of clumping data together with complex behaviors inside rigid objects, which is the classic OOP way, DoD prioritizes keeping raw data super organized, just so the CPU can crunch through it as fast as physically possible. And that brings us to a massive philosophical shift. Take a look at behavior encapsulation on the right. That's the traditional OOP way. It traps objects in these deep, rigid family trees. So if you want a flying enemy, it has to inherit from enemy, which inherits from character, which inherits from moving object. You can see how that gets messy fast. But on the left, we have composition over inheritance, the ECS way. It's honestly like building with Lego bricks. You're dynamically composing complex objects from completely reusable data parts. Looking at this early architecture, you can see a real step in the right direction. But notice how entities, like the bullet, the player, the enemy, they're still awkwardly encapsulating their own data components. If you trace those tangled lines pointing down to the systems, it's pretty clear that true decoupling hadn't quite become the standard yet. The data was still essentially trapped inside the entity itself.
Which leads us perfectly into part 2, the anatomy of an ECS.
Now, welcome to the absolute holy trinity of game architectures, the modern entity component system. Notice the total clean separation we have here? The entities up top, the systems right in the middle, and the components down at the bottom are completely decoupled. Entities, they're now just raw IDs. They hold zero data. Instead, the systems use weight-free hash maps to dynamically pull exactly the component data they need from massive, highly organized storage pools. It is incredibly clean, and man, is it fast. Let's put this into practice. This modularity is just ruthlessly efficient. If we're building a moving player, we just hand it a position, a vector, and a texture. A static wall? That just gets a position and a texture. Because we've separated the data out, our render system simply asks the pool for anything with a position and texture. It'll grab the player and the wall without caring at all what they actually are. The systems are only processing exactly the data they require. No wasted effort. Moving right along to part 3, the concurrency bottleneck. So what happens when you have millions of these tiny components that need to be updated simultaneously within a single game tick? Well, things get really complicated really fast. To process them instantly, developers rely on vectorization. This uses SIMD hardware, single instruction, multiple data. But here is the major catch. For this extreme speed to actually work, every single one of your components must be lined up perfectly back-to-back in contiguous memory. If they are perfectly aligned, the processor can crunch them all at the exact same time, kind of like a massive, highly synchronized industrial assembly line. But to keep that assembly line moving, we absolutely need another vital concept, the wait-free property. When you've got multiple threads working at once, waiting on a locked resource will absolutely kill your performance. A wait-free system guarantees that no thread is ever stuck waiting in line for another thread to finish up. Every single operation is guaranteed to make progress in a finite number of steps, no matter what. To safely manage all these wait-free threads, game engines rely on the tick lifecycle: preparation, execution, and cleanup. You can think of the tick as the literal heartbeat of the simulation. This cycle enforces a strict data guarantee. It creates what we call a serialization point, where all the chaotic, concurrent math from the execution phase is perfectly synced up and applied exactly once per tick during that cleanup phase. But there's a catch, which brings us to part 4, the ABC problem. So we've got perfectly lined up memory and wait-free threads running beautifully every tick. Sounds perfect, right? But this perfectly ordered system has a massive Achilles heel: the ABC problem. Just imagine we have a perfect array of entities that all share components A, B, and C. We are processing them at lightning speed. Then suddenly, halfway through the game tick, one entity loses its B component. It instantly leaves a gap in the array. And that single gap, it destroys our contiguous memory, completely ruining our lightning-fast vectorization. To actually fix this ABC problem, we first need to take a look at finite state machines. Check out this simple diagram of a jumping man FSM. The system uses one specific input, the y-coordinate, to smoothly dictate the transition between two distinct states, standing and jumping. It's simple, but highly predictable. And you can immediately see how this exact FSM concept scales up to manage incredibly complex behaviors. Just look at this AI state machine. The NPC smoothly shifts from patrolling to defending to retreating, based entirely on distinct trackable inputs, things like health levels or enemy proximity. It becomes a closed system with trackable, strictly defined states. Which leads us to our final piece of the puzzle. Part 5, enter the entity FSM. So what actually happens when we combine the lightning-fast data processing of an ECS with those highly trackable state transitions of an FSM? Well, we get the Graph Entity Component System, or GECS. And the real magic here lies in archetypes. Instead of keeping messy individual arrays for every single component, arrays that easily get broken, we group entities into strict archetypes. If 10,000 entities all have components A, B, and C, they belong to the ABC archetype and are stored safely together. This brilliantly and safely restores our contiguous memory and totally saves our vectorization. Notice how GX maps this process out. Adding or deleting a component from an entity isn't some messy memory deletion anymore. It's simply treated as a state transition across this really cool, colorful graph of archetypes. So if an entity in the ABC state loses component C, it simply transitions across an edge on this graph over to the AB state. Clean, simple, and trackable. Now, to achieve a true, fully wait-free model where data isn't physically moving around while threads are trying to read it, GDEX uses ledger-based consolidation. Threads safely log their desired state transitions in isolated, simulated contexts. All those changes just sit patiently waiting in a ledger. Then, at the very end of the tick, during that cleanup serialization point we talked about earlier, they are all safely merged into the real context. No waiting, no locks, and absolutely no stuttering. Which leaves us with this final thought. When developers no longer have to sacrifice game complexity just to maintain performance, when they can actually process millions of dynamic, state-changing entities in perfect harmony using these wait-free graph architectures, what does that mean for the future of gaming? I mean, just imagine the massive, completely lag-free simulations this level of complex computer science makes possible. The next generation of digital worlds won't just look better on the surface. Fundamentally, under the hood, they are going to be built entirely differently. Thanks for joining me on this explainer, and keep exploring.